Okay, so we can begin now. Um, okay, start writing P in the chat window, right? Okay, so we continue with our yesterday's thread. Um, we had um, introduced this Poisson distribution from binomial distribution, and we had a few examples. So although you cannot verify this now mathematically, but he has given you a few sample plots. So if you try to plot the PMF of the Poisson distribution, because mu is the only parameter, yeah, lambda times t, which is mu. So for each mu, you will have a different distribution, right? Because this f of x will um, be written as small p, which is the PMF of the Poisson, then semicolon, then you have this mu, and then you have this x. So x is appearing on the horizontal axis, and then you need one mu for each plot, because without knowing this mu, you don't know what to plot. So it's a parameter. I mean, you can even think of it in this way, right? F p mu of x. Yeah. So the variable is x, but mu is the parameter. Um, and you will see a pattern if you see. So for small values of mu, the distribution is asymmetric, right? So it's to the left, more to the left than to the right. But as soon as you increase the values of mu, what happens is that for a reasonably large value, 5 is not that large, but it's reasonably large, you get a shape which is symmetrical about some mean value, right? So the mean value appears here to be 5. Yeah, it is 5, right? So this also confirms that the meaning of mu is the mean, and you can see that this is the mean, right? Even here you can see it. But because the distribution is asymmetric, so yeah, I mean, it's not very visible, but in this case, you can easily spot it. This is a pattern which you will need later on in another topic. So far, you just needed this to notice this as an observation. And the textbook introduces this connection between binomial and Poisson later on. Yesterday I started with this. So I don't think I need to explain this. Yeah, this was my starting point, that if you start with a binomial random variable, which we write as b x semicolon n comma p, and then you apply these limits, large values of n, small values of p, um, and in such a way that n times p is constant, mu. So then the binomial distribution approaches this Poisson distribution. And remember that I was using theta to avoid this confusion, but he's not using theta. He's using the same symbol p for the parameter, and the same symbol p for the PMF. And anyone who knows how to pay attention to types can deal with this, right? This p is a number, right? Because it's a probability. But this small p is a function. Of course, this, when you apply it to x and mu, you still get a probability. But as far as the symbol p is concerned in this expression, that p is a function, and that's what we call PMF, right? So these two meanings of the symbol can coexist. What is not allowed um, is to have the same type and the same symbol and having two different meanings. That is not allowed. Okay. And there are some more examples. I think it's very similar. So I think I would recommend that you deal with these examples yourself, and I pick some exercise questions, right? So I leave it to you. Let's pick a few questions from the exercise. So let's say I Yeah, let's pick 5.57 randomly. Just random pick. So you're now going to tell me what makes it a problem for the Poisson process, right? So on average, so that's the first thing you need to do. So whenever you see on average, you should think about mu or lambda, right? A textbook author, now he's kind of the experimentalist, makes two word processing errors per page on the first draft of her textbook. So, so now the experiment here is that the author is typing words, right? So the first word, the second word, the third word, and it's in a two-dimensional grid because you are writing words on a page. So you need to have this page as a region of space, right? And yeah, so per page. So instead of per square meter or per square centimeter, you say per page. Per page. Page is that specific region which in most of yesterday's problems it was time interval. Yeah, but this time it is actually a page region of space. And two word processing errors. So obviously, when you are making mistakes or when you are typing errors, those errors are independent. The errors don't ask the previous errors. So you see all those features of a Poisson process, right? So what will be my mu or lambda in this case? Hmm? Can you tell me? We did these things yesterday, right?
2.
So 2 is either mu or lambda, depending on how, if we fix this page, one page, right, then there is no difference between mu and lambda because he's asking the question, what is the probability that on the next page, there is also one page, right? So because there's one page, then you can simply go with mu and you forget about lambda. Um, will She will make four or more errors. So now how do I frame this? Probability. And let's say x is the number of errors. Yeah. So I defined x to be errors per page, right? A random variable. So how do I frame this problem? X here is 4, and what should I write here? Hmm?
Greater than or equal to.
Yeah. So what is the next thing? This is not ready for the table, right? So I will say 1 minus p of x
X less
is
than or equal to 3.
less than what?
3.
No, less than 4 because it's equal to 4. Yeah. So you need the complement, right? The complement of greater than or equal to 4 is less than 4. Now, what you have in mind is that because this is supposed to be a CDF, so you would like to see an equal sign there as well. And that is the reason the 4 must be replaced with
3.
3. Yeah. So 3 is needed because we need a CDF, and x less than 4 was not giving us a CDF. So the rest is just using the table, right? So it will be 1 minus, I'm just writing it there, 1 minus, and this is small p, that was capital P. No, actually, I can use the same capital P. This time it's for CDF. Capital P, the CDF of the Poisson. So semicolon, the mu here is 2, right? And I just write 3 there, and this is what you do from the table, right? Okay, let's, and the part B. What will be part B? P of x equals
0.
0. So what do we do here? There are two ways. Either we use the formula, and the formula was exponential
Minus
minus
lambda
mu
t.
mu to x divided by x factorial. So you just write 0 there, right? So x factorial is 0 factorial. This x is 0. So yeah, you just have exponential minus mu. So exponential minus 2. That's one way of doing it. How about doing it this way? Hmm? How can I express this in terms of a CDF? So it will be p x less than or equal to, tell me. That requires you to know the range of values of x. So in the Poisson process, what are the possible values of x? 0, 1, 2, and so on, right? So 0 is the smallest value. So it doesn't matter whether you write x equal to 0 or whether you write x less than or equal to 0. It's the same thing, right? Because there are no values before. The probability of a negative value is 0. So this is also the CDF, right? This is also the CDF, and the CDF is P of semicolon 2, which is mu, and 0. And you can check it out from the table, right? Let's pick two more questions, right? How about this one, 5.71? So for a certain type of copper wire, you have a copper wire, right? Let's say I'm drawing a copper wire. It is known, so now this is based on historical data about that copper wire. On average, 1.2 flaws occur per millimeter. Yeah, so this is now leading towards Poisson process, right? Normally, I told you that you should be looking for rare occurrences. Rare occurrences remind you of the fact that this probability of success small p is very small, right? So when you look at a copper wire, normally you would not see any flaws, but occasionally you see some flaws, and the frequency or the probability, yeah, of the proportion of those flaws is 1.2 flaws per millimeter, right? So if you define um, um, maybe you define yesterday we were using small t, right? Because we'll use small t anyway, whether it's time or not, because the Poisson distribution is framed in terms of lambda times t, and this t will not always be time. In this case, it's the distance along the wire. So we'll still use t. So if t is in millimeters, right? If t is length in millimeters or distance in millimeters along the wire, then this 1.2 will be equal to lambda, right? Flaws per millimeter. Assuming that the number of flaws is a Poisson random variable, so he's now helping you, although you can assume this yourself as well. What is the probability that no flaws occur in a certain portion of wire of length 5 millimeters? So now how do we solve this problem? You are going to tell me.
So mu will become 1.2 times 5.
Now first we write the expression for x, yeah? So x is the number of flaws, right? I will say flaws. Uh, if I say flaws per millimeter, then I have a problem. Why?
Because that depicts
Yeah,
rate.
because here it's 5 millimeter, right? Then I would require all the questions to be just like in the previous question. We were using the same length. So here, because it's different, so I will not say flaws per millimeter. I will say flaws in any given length. Yeah. So I don't care about the length of the wire. I'm still counting flaws. So it's better to write t here. Yeah. Or you can even say x of t, right? Number of flaws till length t. T is the length. So P of x, and I can write this t here to remind myself that it's not per millimeter, it's just anytime, and no flaws. So equals to 0, right? So that means that I can use simply the PMF, semicolon. What should go here? Here it is 0 obvious, yeah, because here is the value of x. So what should I write here now?
1.2 times 5.
Yeah, because here I need to write, my mind should recall lambda times t. That's the main thing. So lambda is 1.2, right? Lambda is 1.2 and times t is 5, and I'm done, right? The rest doesn't matter whether I use formula or table. That was the main thing. Okay, what is the next part? What is the mean number of flaws in a portion of length 5 millimeters? So what is this question? Mean number of flaws in the same 5 millimeters, right? So it will be,
Just mu that they're asking for.
yes, no, yeah, it is mu, yeah, it is mu, because it is expected value of x, and expected value of x here is mu, right? So it is 1.5 times 1.42 times 5, right?
Mm.
It was easy. Okay. But you need to pay attention to the words. If I change this millimeters to some other units, then you will have to change accordingly. What if I change this, for example, to meters? Let's change this to meter, right? What will I do then?
1.2 times 0.005.
Yeah, so first you need to write 5 in terms of millimeters. So 5 meters have to be written in terms of millimeters, and that will be times 1000. So yeah, of course, this is not a course on units, so I don't think I should be testing you with that. But in case you find it elsewhere, okay. Now we need to look for the next problem, and then we move on to the next topic. Okay, so 5.72, potholes. Yeah, you know potholes on the road. So just like speed bumps are not desired, potholes are not desired either. And when you are going on the road, except you are living in a very bad area, normally on a road, or especially on a highway, right? On a highway, it is very rare to find these potholes because highway is meant to be smooth. So this rareness is the reason why we can apply Poisson process here. Can be a serious problem and are in constant need of repair when with a particular type of terrain and make of concrete. Past experience, so relative frequency approach, suggests that there are on the average 2 potholes per mile after a certain amount of usage. So here, if we use the distance along the road, right? That t will be the distance along the road, um, distance in miles, because here we are talking about miles. So per mile, and then lambda equals 2, right? It is assumed that the Poisson process applies to random variable, the number of potholes. So that is my definition of x. X is the number of potholes. And you see, he doesn't say x is the number of potholes per mile. Yeah, number of potholes means that you can have any number of miles. So you think of it as x at t, and t can be any value. Now, what is the probability that no more than one pothole will appear in a section of 1 mile? So here t is also 1, right? In this part, t is equal to 1. And what is the probability? P that xt is no more than 1.
Less than equal to 1.
Less than or equal to 1, right? So it's simply the CDF. CDF. Now I'm using the CDF notation. Small semicolon, lambda is 2 and t is 1, so it's 2 times 1, right? And here it is 1, 2. This one will appear there, and then you're done. How about part B? What is the probability that no more than 4 potholes will occur in a given section of 5 miles? Here the value of t is 5, right? That's the advantage of using lambda, because you can deal with any number of miles here. So it will be p x t
Less than equal to 4
less than or equal to
without 5.
less than or equal to 4, right? And then it's the CD of at 4, and here you have 2 again. No, here it's not 2. Here is 2 times 5, right?
Yeah,
And here, no. Okay, this 4. This 4 comes here. This 4 comes here. And 2 is lambda. And this 5 comes here. Yeah. So 4 semicolon 2 times 5, right? So this is the advantage of using this t here, because when you write t below x, you somehow can remember what to do. If you simply write t, then you will not have any way of distinguishing between these two parts, right? And that also means that we should be using t. If you want to remind yourself, you can just write that t here as well, mu t. So mu t is actually lambda times t. Yeah, t is just a reminder. Okay. Um, yeah, we are done with this chapter, but I just need to say one thing before we move on. Although that is not part of this course, but you still need to be able to see the difference. So he is using the word, two words in this chapter. One is Poisson, actually three. Yeah, so it's Poisson random variable. Then he is using Poisson distribution, and at the same time he is also using Poisson process. Yeah. So you know distribution, the random variable which we write x, and then we know the distribution. The distribution is the probability distribution, so you can either be talking about the PMF or the CDF. You can use any of these to say distribution is not a unique thing. Yeah, anything related to probabilities, whether it's PMF or CDF, they both qualify to be describing the distribution, right? So it's like if I ask you about your performance in an exam, so you can give me many, yeah, way. It can be expressed in many ways. You can express it in terms of letter grades. You can express it in terms of marks you scored, from things like that. So PDF and PDF, PMF, both are describing the distribution. But what do you mean by process? Yeah, so that is something you need to know. So here, this line is the key, mu equals lambda t. So this actually reminds that mu is actually a function of t, right? So in all these problems, what we have been doing, we fix the value of t. So we know the value of t. Sometimes t is equal to 5, sometimes t is equal to 2. And then we compute the value of mu, and then it becomes a random variable, and we have a distribution, and so on and so forth. The reason we sometimes need to use process is that we would like this t to be a variable instead of being a fixed value, right? So if I now start with the distribution again, small p and x lambda t, let's say that I'm highlighting x and I'm highlighting t. So highlighting means that these will be my variables and lambda will be fixed. Lambda will be a fixed parameter. So if I allow t to vary, then I cannot say that mu is a parameter. Mu cannot be a parameter because mu itself depends on t, and t is a variable. So then I will have one distribution for each value of t, for each value of small t. So it means that I don't have a single random variable. I have multiple random variables, and that is why writing this t here is so important. Yeah. So it means that, for example, if I have t1, I have one random variable, t2, another one, t3, another one, and so on. So instead of write, each of them is a random variable. And if I focus on each one of them, then I have a distribution. But if I talk about all of them together in this form, then it is a process. So the word process has to be used only when you want to keep t as a free variable, just like x. I hope you remember that, right? And none of the examples was doing that. So actually, there is no need to use process in this course. You will need this Poisson process in more advanced courses. So are there any questions so far in the Poisson process?
Sir, I thought that when we would increase the length of time or the time interval, then the probability inside it would increase for a random variable.
Could you say it again? I just
I was saying, when you increase the length of time or
yes,
time
yes.
interval, I thought that the number of occurrences would increase or
Yeah,
the prob.
the average number increased, so the number of occurrences will also increase.
Yeah, but we didn't exactly see that in the examples. It only really increased by a few points, maybe.
Yeah, but if when you compute it, then you will see it. I mean, it will not increase in a predictable manner. Only the probability will increase, right? And you have already seen it in that plot. Let me just show you the plot.
But the probability still stays small, right? Even if
No,
it.
it will be small, but if you compare the two probabilities, you will see the difference.
Yeah.
Yeah, I mean, if you are asking the same question, then you will see the difference. So let me show you that plot again. You must keep this in mind, right? Uh, I know that there's something very funny here that I have to open another page because the I need this application so that I can write on it. But the problem with this is that moving from one page to the next page is a hell. So I need to open PDF and just figure out the page number. Some discrete and whatever it was. Yeah, this. So this page was 183, right?
Yeah.
Let's go to 183. Yeah, here you can see now. If and what you can imagine is that let's say that this 2 is greater than this 0.1, maybe because of time, right? So let's assume that we use the same value of lambda for all these three graphs, right?
Mm.
So let's say lambda is equal to 0.1, and this is 0.1 because t is equal to 1. Yeah. So here lambda times t is 0.1. I'm just cooking it up so that you see the point. Here t is equal to, yeah, 20, right?
Yeah.
So that's why lambda times t is equal to 2. And here t is equal to 50, right?
Yeah.
Okay. So now tell me what will be your question in this case. You think that the probability is not increasing?
It. I mean, not
Yeah,
exactly,
but why do you expect that the probability should increase?
because we're increasing the time interval, right?
No, so you see now you need to understand it mathematically, right? So when you increase t, you need to look at the equation. The reason there is something you can only say about mu, okay?
Mm.
Mu increases with t because this is the plot, right? T increasing, mu also increasing, and lambda is the slope. What is the law for the probability? Write the equation. So it's lambda t, right? And it is x. So now look at the formula. It is
Exponential.
exponential minus lambda t, right? Lambda t to x factorial. Now this equation is too complicated for you to say that it should increase with t, right? It's not a
Yeah.
linear equation. It's a non-linear equation. And how does the probability change? You have to just compute every time. And the probability has to be between 0 and 1 anyway. So, yeah.
But we did establish before that the number of occurrences are proportional to lambda t. to
Yeah,
delta.
the mean. You can only say that about the mean number of occurrences, mean.
Okay.
Yeah. And if you replace the mean number of occurrences by number of occurrences, then you have to use x. And x is a random variable, and you cannot know the value of random variable, right?
Yeah.
So all you can say is either the mean or the variance or the probability. So you need to be careful with these arguments, right? If it was so simple, then we would not be doing probability. We would be using it just like calculus. Yeah.
Yeah.
So you need to remember what you can say and what you can't say. The probability actually spreads out somehow. Yeah. It's like the total probability is one, and the reason we are calling it distribution is that the probability literally distributes to these values, right?
Mm.
Yeah. So you can think of it as someone sharing, yeah, that constant probability among these different values. So if you have more values, you can see here. Here you have a larger peak here, and here the peak is smaller, right? So why is the peak smaller? Because now there are more values, and the same probability has to be given to a larger number of values, right? So that argument of increasing probability, you compute probability at each value. Yeah. So at each value, sometimes you will get a large probability, sometimes you get a small probability, right?
Mm. Makes sense.
Okay. So let's get to. So we are done with discrete random variables so far in this course. Um, Although we did not have an example for the variance, but what you should remember is that the mean and the variance both of the Poisson process, right? Of the Poisson distribution. If I write an x here and x is Poisson, so I simply say x is Poisson. People typically write this symbol for distribution. So Poisson distributed, um, then and yeah, the Poisson distribution needs lambda and t, right? So both the mean and the variance will be equal to lambda times t. That's what you need to remember. So if there is any question about variance, you can simply use this formula. Okay, so we can now begin continuous probability distributions. So far in this course, we have seen um, some common families of distribution. The reason we use the word family is that each of these distribution has a parameter. So for example, if I talk about binomial distribution, it is not correct to say binomial distribution. It's actually more correct to say binomial family of distributions. Why? Because it's not one distribution, it is a family of distributions. And why do we say that? Because the binomial, if I write that small b, I write small x here, so this is a variable, and then I write small n and small p. So for each value of n and p, I will have a different distribution. So that is why, but all of them have one thing in common, that all of them follow this pattern. Yeah. So you change the value of n and p, then you get a different probability distribution, and they all are called members of this family, right? And similarly with the other geometric, hypergeometric, negative binomial, yeah, and Poisson. But they all were discrete, right? Discrete. And you know the meaning of discrete random variable, yeah, where the particular values assumed by the random variable has to be a specific, it has to come from a countable, yeah. So it has to be a countable set of values from which you pick the um, yeah, from which you pick the values of x, and then you get the distribution. And that is why the plots always look like this. Yeah. So you have values of x, and for each value of x you have a probability. So you use the word PMF for discrete random variables. Okay, so now we are ready to move on to the next chapter, and that is about continuous probability distributions. We know how to deal with continuous probability distribution. We need PDF and then CDF, and the set of values is uncountable. We know that. But what we need in this chapter is that there are some common distributions just which are continuous, and we need to be aware of them. Okay, similar to the list we had for discrete, like we had geometric, hypergeometric, Poisson. So we need a similar list of common distributions for continuous. And the most common distribution you see in literature is called the uniform distribution. Uniform. The reason we call it uniform is that if we think of an axis along which you have these values, right? This is a real line, and we use x for the possible values. And let's say, for sake of simplicity, uh, the possible values are in this interval. So you have a value a and then a value b, and the only possible values are in this interval, right? So if you now plot the PDF, right? PDF. We need PDF because we are talking about a continuous random variable, right? So if it was discrete, we would be talking about PMF. So if we plot the PDF and the PDF turns out to be a flat line, right? A flat line, not changing, right? So what will be the value of this PDF before A? Hmm? Can you tell me?
The same as for B
No, no, before A here,
or before A.
for this region and for this region.
Probably 0
It has to be 0. Why?
because that's how like PMF and PDF work.
Yeah, because I told you that these are the possible values. The possible values have to be in this interval. So if these values are not possible, they must have a 0 PDF. Because if they don't have a 0 PDF, you will integrate that region and then you will get a non-zero probability. So if you get a non-zero probability, then how can you say that they're impossible values, right?
Yeah.
So any value that is impossible must, you need to keep one thing in mind. These are values of random variable x, right? X. And whenever we ask a question about x, x belonging to some set, right? Some set A, we always take it back to the sample space. And any value which is not possible here will map back to the empty set, and the probability of empty set has to be 0, right? That's the reason PDF also needs to be 0. Uh, so uniform doesn't mean that it has to be uniform throughout the x-axis, yeah, because that is not possible, right? You cannot have the total probability has to be 1. So if I, for example, say that no, the PDF has to be constant throughout this real line, right? No matter how small I choose this value, I have a problem, because then what is the integral of this from minus infinity to plus infinity? Dx, even if this is really, really small, right? Tiny, small. What will be the integral? Hmm? I have this problem again. I clicked something and now I need to can I go to previous page? This doesn't show me the previous page, so I have to somehow look there again. And it's 190. This is horrible. It's very, what is this?
Is it something with your mouse, maybe?
No, no, no. Actually, this, I'm not used to this. That's the whole thing. I don't use it on a daily basis, so I will use it only for teaching. 191, right? Okay. So now, what was I asking? I'm telling you that if I use a fixed value of the PDF from minus infinity to plus infinity, not changing it, and I take that as the meaning of uniform. Uniform mean not changing. No matter how small I choose this value, right? What will be the integral? The integral cannot be finite. It has to be infinite. Why?
Infinite.
Because yeah, because it has an infinite length. So no matter how small, as I mean, because this will be larger than zero, so you cannot have. We need the maximum probability has to be one. So the only way that is possible is to have a limited, right, range of values. So that is why we need these two values, a and b, right? And there you can have a fixed value. So now if I ask you what should be this value, we needed this value of PDF to be fixed from a to b and zero everywhere else. So what should be this fixed value for it to be a valid PDF? You know it from previous chapters. What is the requirement that this integral, right, from minus infinity to plus infinity of the PDF, let's call it small f, right? This integral must equal, tell me,
One.
1. And now let's say this value is m, right? Let's call this m, right? I can use any other symbol. So now I will use the integral from minus infinity to a is 0. So the actual limits are from a to b, right? And here the value of f is m, right?
M.
So what do I get here? M
One.
times b minus a, right? So what is m? What is the value of m now? 1 over b minus a, right? That's the only acceptable value.
Also, it's fixed.
Huh? And it has to be fixed, right? So now you can see why we have this definition. The uniform distribution has to be equal to 1 over b minus a, right? Because you will always have a smaller and a larger value throughout that region, right? And 0 elsewhere. That is the only acceptable definition of a. I don't want to say uniform distribution. I should say uniform family of distribution because for each value of a and b, you will have a different distribution, right? And some people want to fix these values too. So there is something called a standard distribution, standard uniform, not just any uniform, but so in standard uniform distribution, they choose this a to be 0 and they choose this b to be 1, and then this is 0 and this is 1. And then what do you have here? So if I choose that 1, 0, right? X is from 0 to 1 and elsewhere. That is the standard uniform distribution. And the reason I'm mentioning it is that there is a symbol for that. So instead of f, then people simply use u. So u of x, right? Here we are not using 0, 1, so you can use a general symbol f. You can also use a small u if you want, because a and b will be there anyway. So you can say u of x a b, u for uniform, and then capital U will be for the CDF, right? So this is how it will look like. So can you now tell me? Can you now explain this graph? Why do we have 1/2 as the value? Hmm? Because this is the value of A, right? This is the value of B, and this needs to be 1 over.
3 minus 1.
So 1 over 3 minus 1 is 1/2. There is no other way, right? Yeah, here is another example, right? You choose A to be 0, B to be 4, and then it's 1 over 4. And you can, yeah, compute other probabilities. For example, if you want P x greater than or equal to 3, then you have this, right? You compute it from 3 to 4. Yeah. Of course, you will start with 3 to infinity because it's greater than, but later on you realize that there is no value other larger than 4, so it's essentially 3 to 4, right? And if you want to compute the mean and variance, you can prove these formulas yourself, right? A plus b. So, I mean, proving this is very easy. I just give you a sketch and you can do the rest. So mu, you know, it will be expected value of x, and expected value of x for continuous random distribution will be minus infinity plus infinity. Do you recall the formula? X times f of x dx, right? And then what is f of x here? 1 over
B minus A.
minus a in that region. So you change the region to a to b dx, and you have to write this x. So you integrate this and you should get this thing. And similarly, you can get sigma squared in that way, right? So instead of proving this like calculus, I mean, there is something you can do later. Let's think about these expressions because that is more important. Um, just like we had to think about, if I now compare this with the mean and variance of the Poisson, what were the values for the Poisson? Now I'm writing it for the Poisson. The mean and variance both were equal to lambda times t, right? So here you can say, okay, if I increase lambda or t or both, I'll get a larger and larger value of mu and a larger and larger value of variance. So you can, I mean, that's the only interpretation you can have in mind. So if you want to say the same thing about uniform, so you say, okay, the mean value is the arithmetic mean of the two values. Yeah. So if I take these two values, 1 and 3, this will just be in the middle. And it makes sense, yeah. Half of the probability is here, half of the probability is here. So, and this is 0. So that is the only acceptable way. Um, and the variance, so this was easy to interpret. The variance has a b minus a in it, yeah. So you can easily make sense of it if I compare two distributions. Let's say one is this and one is this. Yeah, which one has a larger? Which one should have a larger variance? This one, right? Because there is more variation. The possible values spread out over a larger interval. So you would expect the variance to be large, right? Okay. Mm. Can you recall something from the chapters where we did not start distributions? Yeah, we did not introduce discrete random variable or continuous random variable. We did not know PMF, PDF. We were just using probabilities, right? Bayesian rule, law of total probability. There, we were commonly using a rule. So can you connect this uniform distribution with one of the rules we used earlier before there was any mention of random variables? What does this uniform remind you in terms of those assumptions?
Which assumptions?
So try to recall how we assigned probabilities. There were different ways of assigning probabilities. Can you recall? One of them, I'll help you with one of them. One of them was relative frequency, right? What was the other one? Don't you recall equally likely, right?
Yeah.
So can you now see any connection between uniform distribution and equally likely outcomes?
Yeah, because the PDF doesn't change.
Yeah. So here I'm now telling you a typical problem which students have, right? So first, I will have this in mind. So I have this value, let's say choose those values 1 and 3, right? In the example, and then this would be 1/2, right? 1/2. So can I say that each point, because there are multiple points between 1 and 3, right? This is continuous. Can I say that each point will have the same probability? So can I say that probability of x equals, for example, 1, probability of x equals 3, right? And probability of, let's say, x equals some value here, let's say 2, right? All these three must be the same, right? Is that what we mean by equally likely here?
Yeah.
Think about it. It's not correct. There's something seriously wrong with this way of looking at it. What is the meaning of this thing on the y-axis for a continuous variable? What do we plot on the y-axis?
The density.
Density, PDF. And what is this?
It's the probability.
Yeah. So you cannot
So
use this probability. What will be the probability for all of these? They will be the same, but not half. It will be,
we'd have to integrate.
yeah, we have to integrate. And now tell me. So now let's do it this way, okay? So if I have pick any two values, right? Right? So what would be the probability between A and B? It doesn't matter whether you include A and B or not in continuous. So it will be from A to B.
1/2.
So 1/2 in this case, right? Although there is nothing special about 1/2, we can say it about any PDF. And 1/2, and it would be B minus A, right?
Yeah.
So now
So
apply this rule to all of these three. What should be the answer? Hmm?
how do you mean exactly?
No, just apply what I've tried to do here. You have to apply it to these calculations. So let's say I want to do this. P of x equals 2, for example. What will I do? I first have to express this in this way, right? Hmm?
2
Right?
plus small delta x, maybe.
No, just 2, 2. I mean, it's the same. Huh?
Mm.
So it is 0.
Oh yeah, probability at a point is 0.
Yeah. This will be the case for any continuous random variable
Yeah.
because the length is 0 here. Okay. This was not the case in discrete. If this was a discrete random variable, what would we do? We would do this px equals 2, and then we would do this. Yeah. Because there it matters. So we will say less than or equal to 2 and no, less than or equal to 2. And what did we do there? Less than 1, right? Greater than 1. And then we say, okay, CDF at 2, right? Minus CDF at 1. You remember that?
Yeah.
We can't do that here because here, I mean, there you had to keep a distance. 1 and 2 are separate values. Here you are, here you have all possible values. So the interval length is 0 for this one single value. So just remember this: the PDF will, sorry, the probability will always be 0 at a single point, regardless of which random variable, which continuous random variable you are talking about, whether it's uniform, whether it's any other. Yeah, even if you don't know the PDF, it will be 0. That was the reason we needed to introduce PDF, right? And what was the definition of PDF? If you recall, the PDF was actually probability in that tiny range, right? divided by the tiny range. So actually, you can think of it as the probability n that delta x divided by, and that is why we're calling it density, right? A similar situation occurs in this signal systems, right? So there, when you are dealing with an aperiodic function, the Fourier coefficients must be zero, just like the PMF. And that is why you need Fourier transform there, right? So the PDF here in this course is similar to the Fourier transform in that course, and the PMF here is similar to um, the Fourier coefficients in that course, right? Okay, so the next distribution we need to um, discuss in this course is what is called the normal distribution, right? Uh, so normal distribution has a long history, right? It has many faces. So I'll just give you a, a very quick. Um, I mean, it will not be a derivation, but we need a root which was similar to, just like we started with binomial, and under certain assumptions we arrived at Poisson, right? And the assumptions were this: n being very large and p very small in such a way that n times p was a constant, right? That was the main thing there. So sometimes you have a binomial distribution, uh, and this is true, n is very large. Uh, but what you have is that um, there was something else. Uh, yeah, I simply forgot that reasoning. But there was another condition about n times p as well. So n times p and n times p times 1 minus p. I mean, something else is also very large, and then in this Poisson doesn't work. So you somehow end up at a at what we call the normal distribution. So I mean, the argument here requires lots and lots of facts. So I don't think you will be able to remember that. So we just start this as a given thing. Um, Historically, people have been seeing a curve which they call normal curve, right? Uh, Another name which you will find in the literature is called the bell curve. If you search the internet, you will see bell curve and normal curve. Yeah. So the typical observation is this. So that I would say that in a large number of quantities in nature, when they vary randomly and when they are continuous, of course, it's continuous. So what people have observed is that you have this typical shape, um, that you have a symmetric distribution, continuous, and the mean value is always at the center. Not only at the center, you have a peak at the center, and then the probability simply rolls off smoothly, and there is no end. It can go all the way unlimited and all the way unlimited there. Whenever you see this bell curve, I think the guy was Bell, or the reason it's called bell curve is something like that. Um, so, so the random variable attached to this is called a normal random variable. That's what you can now remember. So a continuous random variable which has a bell-shaped distribution, right? Um, just like in figure 6.2, will be called a random normal random variable. And just like we were using small p for Poisson and small b for binomial, we can use small n for normal, the PDF, of course. And if you use small n for the PDF, you will use capital N for the CDF, right? Capital N will be for the CDF, small n will be for the PDF. of a normal distribution. And you need two parameters. One of them is the mean, just like you had it in the Poisson, and one of them is the variance, right? Sigma, the standard deviation, sorry. Sigma is the standard deviation, and that standard deviation also becomes a parameter. And then you have this formula. An argument which, yeah, I can now recall an argument, okay? So that will not be very complete, but I think it should be something for you to remember. So let's say you are investigating a random variable, right? And we call it x. And let me give you an example. Let's say we are investigating the uh, length of a plant, a particular plant. I focus on a particular plant and I collect samples, right? Some plants of that family happen to be have this length, some plant have this length, some plants have this length. So if I now um, see a histogram of these lengths, so I will see this bell-shaped curve, right? And if I want to see this as a continuous, because length is a continuous variable, so I will observe this bell-shaped curve. And one of the ways in which it can be explained is this: the the factors responsible for the length, because length has to come from different pieces, right? And each piece will have some chemical or physical phenomena behind it, right? So if you think of all those processes as independent, now I'm skipping lots and lots of details. Let's say you have independent variables, many of them. Let's call them, instead of x, we are calling them x1, x2, x3, a large number of variables, each one of them contributing to this final x, right? And then we have actually an average as well. So let's say you do it till some large value n, and then you divide it by n. So whenever we are averaging um, a list of variables, they are all independent. So you need to remember something: independent and identical, just like we had in Bernoulli process, identically distributed random variables. We have a large number of independent and identically random variables, and we take the average of that. Someone mathematically proved that distribution of this, if you take this limit, if you allow n to be extremely large, then no matter what is the distribution, you don't even need to know these distributions. You just need to know two things: independent, identical, and large number. The amazing thing is that all of these cases merge to the normal distribution. And that is why it is so popular, right? So I think this is the most common argument you will see in the literature. So apart from the reasoning, we need to be able to apply, right? This to problems. So you can only apply this to continuous variables. That's what you need to remember. And if the continuous variable happens to have that bell-shaped curve, you can then apply it. Um, okay, so pay attention to this formula. This formula has exponential, right? And you know the value of the exponential. This formula also has a pi in it, and that pi multiplies 2, and then you take the square root. This sigma, which is the variance and the standard deviation, this will appear in the denominator here. And remember that this square root actually stops before sigma, yeah? So sigma is not part of the square root. And then you have this sigma squared in the denominator here in the exponent, and then x minus mu squared. I think that if you look at this formula and all possible values, every real value is possible, yeah? You go from minus infinity to plus infinity. Okay, this shape is very interesting because this is a PDF, we know it's a PDF, right? Density. So if you integrate this, you'll get something. Let me integrate this. So I integrate from minus infinity to plus infinity, 1 over 2 pi sigma minus 2 sigma squared x minus mu squared dx. And here I assume that I have fixed sigma and mu. These are parameters. So that you need to fix them before you integrate this. This integral will turn out to be 1 because this is the density, right? I want you to think about this shape and think about this formula. Um, and to make this simple, I'll choose mu, because if you look at this graph, it is very difficult. So let's choose mu to be 0 and sigma to be 1. So let's say sigma is 1, mu is 0. So I can get a simple formula. So this formula becomes 1 over 2 pi square rooted. Sigma is 1, so I don't write that down. Exponential minus, I just need half because sigma is 1 again. Mu is 0, so I just write sigma x squared. So 1 over 2 pi square rooted exponential minus x squared half. If this was not squared, right, then this shape would look like this, because you know how the exponential looks like, yeah. It will look something like this with a negative one. And if this was positive, it would look something like that, right? But instead of these two, you see this roundabout shape is because of the squaring nature. That is one consequence. And because of the square, this roll off is very sharp. If it was not square, then the roll off would have been a little smoother, yeah? Things like that. So that's what you can now imagine. So let's say I don't change mu, right? I don't change mu and I increase sigma. So I will have a curve like that. Can you tell me why do I have to decrease this height if I want to increase sigma? What will be the reason behind that? Hmm?
Because the overall area has to stay the
Yeah,
same.
the over probability has to be 1, right? So these are the extremes, yeah? This is one extreme where it literally becomes 0. What will be the other extreme if I keep decreasing sigma? What will happen?
It will become an impulse at mu.
It will get taller in the center, but it has to be narrower. Why? Because
For
again, the total area cannot exceed. So if I make it tall, if I make it narrow horizontally, it has to become tall vertically. Otherwise, I cannot get that area of 1. So what will be the limit if I apply a limit sigma approaching infinity? What do you get of this quantity, which is 1 over 2 pi square rooted exponential minus x squared by 2? What will be the limit here? You know the answer from another course. What happens to the width of this distribution?
maybe it goes to 0 because
I think I made it wrong. This sigma is 0, right? I should not have said that. So you approach sigma to the 0. Yeah. You make it vanishingly narrow, so the height will go infinitely large, and it will look like this thing. That is simply your delta, right? Delta of x, the one you see in signal system, Dirac delta. The reason we are calling it delta is not just because it becomes infinite. That's only one reason. What is the other reason? The area is,
yeah, the area is 1.
yeah. So area has to be 1. Infinite is not enough. Okay. So it has to be narrow. The area has to be 1. Um, and only then you can call it delta. Now this is the significance of having different means. Okay, so for now remove all these annotations. You need to be able to make sense of such plots. So that was one way of investigating it, where I simply make I don't change the mean, I just change the standard deviation, and I can have different distributions. Some will have a larger uncertainty, more uncertainty. Some will have less uncertainty, right? But this is another way of investigating it. Don't change the width, right? So you have the same uncertainty, but this time the mean value is different. Yeah? So you have one uncertainty about mu1 and another uncertainty about mu2, and these two distributions have the same uncertainty, right? Only the mean is different. And here, this is what I was trying to do. The same mean, but different uncertainties. So uh, which graph has a larger uncertainty here?
Mu2.
Yeah, the one with mu2, yeah. So you must have two random variables, x1 and x2. So x1 is corresponding to sigma 1, x2 is corresponding to sigma 2, because sigma 2 is not a random variable, it's just a parameter. And here you have both, yeah. So not only the means are different, but the variances are also different. Yeah. So here in the second plot, not only the mean is larger than the previous one, but it has a larger uncertainty.
So the different curves are formed with different random variables.
Yeah, yeah. So you cannot have the same. You cannot have one random variable with these two plots.
Yeah,
Yeah. So they are different variables, but they belong to the same family. And what is that family?
the normal
Normal. Yeah. So
distribution.
normal is the name of the family actually. Normal distribution. And because Gauss was the guy who investigated it, so it's also called Gaussian distribution, right? It's the same Gauss who was very famous, yeah, in Germany.
Mm. So, but when we add the different distributions, then we get another normal distribution and
Yes,
divided
yeah,
by
but
the
you know it from previous chapter, right?
yeah.
Yeah, I mean we learned how to compute the expected value of a sum of random variables, huh? And there is even an interesting thing, but we didn't study that. The interesting thing is that if you have one random variable x1 and there is another random variable x2, right? And they will have their own distributions, right? Even if you don't know the distribution, but you just have to assume that they have some distribution. You add the two and you get another random variable. Let's call it x. Now, the amazing thing is that the distribution of x can be related to these two distributions, and that turns out to be convolution. So if this is, let's say, continuous, so it will have small f1, right? Small f1 will be the distribution of x1. Small f2 will be the distribution of x2, the PDF I mean. And let's say small f is the distribution of x. So you can show mathematically that this will be convolution, the convolution you had in signals and systems, right? And if they are discrete, it will still be convolution, because you can have discrete time convolution and you can have continuous time convolution. Uh, you won't believe, but convolution was first discovered for random variables. Yeah, it was applied to signal and systems later on. So this is the first time people saw convolution, right?
So it's the convolution of the probabilities.
The no, say it like this: the PDF, yeah,
Mm.
of a sum of two random variables is the convolution of the PDFs of, or you can say the individual PDFs. Right? So don't say that the random variable is the convolution. Yeah, we cannot say x
PDF.
is x1 star x2, right? That's not what we mean to say. The PDFs convolve, and the reason for that is the sum. Unfortunately, we don't have this as our one of the topics. Otherwise, proving this is not very difficult. So, but I don't want to get into that direction. You can just remember it somehow. Okay. Do you remember? Uh, I think it was Chebyshev. It was some strange spelling, right? Chebyshev inequality, right? It was that the probability that x minus mu, yeah, the absolute value is larger than some value k has to be greater than or equal to 1 minus 1 over k squared, is something like that, right? So you can link that inequality here, right? So if you move away from this distribution, just pay attention. Let's say I want to know the probability in this interval, right? So let's say this is mu, and because I know this is sigma, so what will be this? This will be mu plus,
Sigma.
and this will be
Mu minus sigma.
mu minus sigma. So this will be certain area. You can even compute it, right? So if you now increase this and you turn it to 2 sigma, right? Mu plus 2 sigma, mu minus 2 sigma. I think that it was like that. I remember it now. It was probability of that x. Now I remember it correctly. That x is between mu plus k sigma, right? And mu minus k sigma. Instead of 1 sigma and 2 sigma, you just write k sigma, right? So I can simply write k here. K can be anything between. So minus k. This turned out to be greater than or equal to 1 minus 1 over k squared. So there, yeah, I mean, we saw that if k is 3, for example, if I replace this with 3, this value was nearly equal to 89%. I remember it was something like that. But this didn't require us to know the PDF. It can be any PDF. This can even be a discrete random variable. Remember that inequality was true for all random variables, because such a question can be asked for discrete as well as continuous. But what we can do for a normal distribution is much more than that. Because what is the advantage here? We know the distribution, we know the PDF, so we can actually compute this. Here he could not compute, he could only give ranges or bounds. So if you try this for normal distribution, it turns out that for 3 sigma and 3 sigma, mu minus 3 sigma, mu plus 3 sigma, this probability is actually 99%, actually more than 99%. That's amazing, right? And for 1 sigma, it is 68%. For 2 sigma, it is, I don't know, 95%. You should search it in the internet, right? And you will see. I mean, I can just do it here quickly. Um, 3 sigma, yeah, normal 3 sigma, normal distribution 3 sigma, and you will see this plot. Yeah, look at this now. So this 34.1% and 34.1%. If you add the two, what do you get? 68.2%. You have it in 1 sigma, right? Plus minus 1 sigma. Can you see that? And then when you add another sigma plus minus, you add 13.6 and 13.6 to both sides. So if you add all these four values, it is something like, yeah, it's I, I cannot do it in my head, but you can imagine it will be larger than 90. And if you add the remaining, yeah, sigma, so then it crosses 99 point something. Yeah, so one is 99.7 and yeah, the other is 95, right? The 95. Okay. And one other thing you need to remember is that this center mu is not only the mean, but it is also the mode. Yeah, because it's the highest PDF. So the mode of of a continuous random variable is described by the peak, the highest value of the. It is the value of x for which the PDF is the highest. Don't say probability because probability is zero. Yeah, and you can prove that the mean is sigma and the variance is sigma squared. And I leave the proof to you because we have been doing these proofs in previous chapters, right? You just use the definition. Yeah, area under the normal curve. Okay. So if you want to, let's say, compute probabilities, let's say you want to fix two values, x1 and x2, or a and b, and you want this probability, you just integrate from x1 to x2 because that's how you compute probabilities, and then you integrate this, and this should be the shaded region. Now, we don't want to compute this every time because this is not a nice integral, right? You can't do it with your calculus formulas. So it's better to have tables, right? So now having tables for different values of mu and sigma is not practical, right? Because you will have one table for each value of mu and sigma. Then you have actually, you need an infinite number of tables. So now this requires some algebra. And there is an interesting thing. Just a while ago, you asked, yeah, if you have two random variables and you add them, right? You get another random variable. So here, if we have a random variable x, and all we need to do is to subtract the mean from it and then divide by the standard deviation, you get a new random variable. And that is called standardized random variable because this random variable z will be standard. In which sense? Let me ask you, what is the expected value of this thing, x minus mu over sigma? What can we do here? First, I write this as a linear combination, right? So x 1 over sigma minus mu over sigma. Yeah, so I can think of this as a times x plus b. B is minus mu over sigma. So I know expectation of ax plus b is a expectation of x plus b, right? We had this formula before the session. So it will simply be 1 over sigma times e of x, sorry, minus mu over sigma. And what is e of x? Sigma, right? Sorry, e of x is mu. So mu over sigma minus mu over sigma. So what do I get? 0. So the first thing we need to know is that if we have this transformation, we know the mean will be 0. So I don't need to know the mean. I just change the mean to 0 because I want to have tables for this variable. I don't want to have tables for x. I want to have tables for z, right? And what is the standard deviation? Even that, for that I have a formula. Let's recall that. What was the variance of ax plus b? I remember it was a times the variance of x. It was actually square, and b had no role to play, right? So because in this case, I can write this as, so I'll just write now variance of x minus mu over sigma. So it will simply be the variance of x times 1 over sigma squared, right? because this a squared is 1 over sigma squared. But variance suffix I already know is sigma squared. So sigma squared divided by sigma squared is 1. So it's amazing. If you make this transformation, if you apply this transformation, all the variables can get converted to a single variable which has a mean of 0 and standard deviation of 1. That is why it was called standard normal, right? So what is standard normal? Standard normal is a normal random variable which has a mean of 0 and a variance of 1. And because now we know the mean of and variance, we can have just one table. So we will have one table for normal, and every other variable will be expressed in terms of a normal variable. So now, how can I invert this? Let's say I have a table for the standard variable z, right? So I can now express this x in terms of z. So x is sigma times z plus mu, right? I can now take this sigma to the other side, it gets multiplied, and I take this minus mu to the other side. So I can now use this formula because I can deal with z, so I can then recover x from z in that way, right? So standard normal distribution. The distribution of a normal random variable will mean 0 and 1 is called standard random variable. Okay, I think we are done, right? So write your name, roll number in the chat window.